and see how that particles would work in space. That's one thing we can probably try. And we also need to build some, satellite hardware that is very close to the real satellites, right? I think Mengwei is working on that. And the good news is that if you look at the Starlink satellites, they are using the commodity hardware. They are not using specialized satellite hardware, which use specific, specialized CPU for the hardening of to be more resistant to the radiations. So that basically means that even if we use commodity hardware on terrestrial network, we still can have some level of fidelity in evaluate it. Of course, that definitely needs more efforts from system researchers to build a realistic system. I think there are definitely many different opportunities that this system researchers can contribute to building an open platform for us to test and evaluate the satellite protocols. Thank you.
Okay, thanks.
Yeah, actually, I think Yuanjie pretty covers what I want to say. So actually, I feel the satellite network research kind of reminds me of the federated learning research, because the federated learning system needs to be deployed to 1,000 or millions of devices, which researchers do not have, right? So the status quo is that we provide some device training numbers on real devices. Then you plug in those numbers to a simulator as a hybrid manner. So I think that's also the way where the satellite research community is going. But I think the hardest part is that how to prove that those simulator behaves closely to the real constellations like Starlink. I think that needs more work and more effort from the community, maybe probably more from the industrial partners, that we jointly build a system that people can rely on.
Yeah. Okay. Mike, since you already did Starlink.sx, which kind of simulates your Starlink network, do you have any thoughts?
Yes. So I think on one hand, these constellations carry a massive amount of engineering effort to build, and a massive cost. I mean, Starlink by Elon's own postings is going to cost about $10 billion to build. I would say that any budget that you ever do on anything usually slips. So it wouldn't be unreasonable to think that this could grow to $15 billion, which is a huge amount of money. Now, the technical complexity means that research, in my particular case, I'm interested in pretty much reverse engineering how the constellation works and finding out what it is capable to do and what it isn't. And a lot of the data comes from things like FCC filings and FCC proceedings and documents filed with regulators. For example, the gateway locations are not made public, so you have to use satellite imagery and regulator websites to effectively hunt these gateways and figure out where they are. How the inter-satellite links operate and work is another mystery. I mean, they do work. I have personally tested terminals in areas without gateways, but when you see, for example, 400 milliseconds of latency, my assumption is that the data, basically the traffic is being carried up to the satellite and then around an ISL path across the constellation, eventually landing in a gateway, and then making its way through terrestrial networks to the point of presence where my particular connection is homed. But then someone said, well, what if it's actually going through the laser mesh, a lot of doing a lot of hops through the laser mesh, and that's causing the high latency, which is a valid question. So, and the short answer is there's no real way of knowing what path it's actually taking. So there's a lot of things that you can find out. There are others that you cannot, and some that you need to infer from experience, calculated guesses, and publicly available information. So it's not easy to study some aspects of these constellations. Some also require considerable resources. Like if you need to observe the constellation simultaneously from different points on Earth, you need a very highly coordinated effort with multiple terminals, with time synchronization to make sure that you're logging all the data with accurate time stamping. So it becomes a fairly significant problem. It's not about I point an antenna at a stationary satellite, geostationary satellite, and measure the signals coming off it, or do some analysis that way. You have a highly dynamic system, which is also changing on a daily basis because they keep launching satellites, and these satellites are adjusting their orbit heights and coming in and out of their orbital position. So it's definitely a very interesting thing, a very interesting area of research, because it's all new and there's a lot of things to dig into, but it's also very complex in other ways.
Thank you. Paulo, you're coming from an industrial Airbus perspective. I'm curious about how Airbus is engaging with researchers, or is there any internal Airbus ongoings that you can safely share with the audience on how they are emulating or simulating these networks?
Okay. Just starting from more generic point of view, my understanding is the problem that we are facing, that the other panelists already described quite well, about the need and the, let's say, the problem of replicating a real system is the same thing that we are facing in the internet for the last 40 years, right? So a long time ago, there were projects like Planet Lab, where people were facing the problem, how does the internet works, right? And the only thing that we could do is to do end-to-end traces using TCP or other transport protocols and trying to figure out what's happening inside the network, because no one could hack or just anchor a router in the core of a tier 1 operator, right, to figure out how does that work. So the same thing happened with LEO constellations. It's a global network, very complicated, very complex, and most likely we are going to face the same problem. Right? I don't think we are going to be able to have a full-fledged realistic emulator for several reasons. First, because there are things that are there not to be known. Like Mike said, how the intersatellite links, optical links work, the precise let's say configurations of the optical terminals, or how is routing done inside the terminal, right? It's just a very dumb pass and forward or some more complicated one. This kind of information is not going to be released. So we need to go back and figure out, or to redo what we did with the internet. And I think emulators like StackNet, that was already mentioned here, I think they are very, very good, let's say, tool to be used by the research community. Within Airbus, we actually are facing more or less the same problem, because, like I said, I'm working on a research center, and sometimes we are not also having the full information that relate with products that are going to be released. So we also need to rely on emulators. And so the emulators that we use internally may be, let's say, in some degree comparable what was already mentioned by other panelists like SavvyNet and others, right? That are full-fledged or full software emulators, or they actually include some hardware in the middle that we can actually put there. So we are in the same, let's say, boat, everyone. So the question here is, I think will be a dream that we will be able to test. So I could dream to have like a CubeSat scientific, let's say, infrastructure in space that everyone could upload the code that you want them tested, right? Kind of software-defined networking kind of thing, where you could upload any kind of routing algorithms, data forwarding, error correction algorithm, whatever that you want to try. Of course, you cannot change lots of things like the hardware itself, right? Some of them is already reconfigurable, like I said, in the one side is reconfigurable. So all of these things could work, but it comes with a price, right? So I can imagine the price of launching a scientific constellation with a small number of satellites for be used by the international community. That will be kind of a very nice global effort to see. Besides this, I think the way to go is to use as let's say realistic as possible emulators, including some real equipment, right, in the middle, and at the end of the outcome of the scientific work is to give us ideas how can we do later on. Actually, most likely not on the real system, right? So that I think that will be the same thing all over again, like what we saw in the internet. I don't see the problem as being a different one. It's exactly the same problem that we need as scientists and as research that we are facing since ever. Right?
Thanks, Paulo. So let's open the floor for audience questions. Does anybody have any questions for our panelists? Yeah, Arash, please go ahead. Yeah. I mean, I can also repeat it from here if somebody.
Okay. So one of the panelists mentioned that the delay is 400 millisecond, and there's a guess that the reason behind it is basically the packet goes around in the ISL links, but it's hard to identify that. And I was wondering, is it possible to just look at I mean, eventually the packet comes to a ground station, and that ground station is located somewhere in the earth. Isn't it possible to just like trace which ground station is the packet coming from, and then from that you could determine how many ISL links have gone over that basically have been used to hop to that specific ground station?
Yeah, so the question is I mean has several steps to it. The first one is you need to try and in your mind basically make your best assumption as to how you would engineer a network like Starlink. And I've always had the assumption, and actually I think it was Telesat actually licensed a technology developed by Google Loon, which was one of the projects that got shut down. And the actual technology for this balloon constellation that's constantly moving, constantly changing in balloon-to-balloon links, but also gateway links constantly changing and user links changing, which is exactly what Starlink is doing. So that technology was licensed. And it pretty much works on a modified LTE stack. And if you look at an LTE stack, what's happening is your subscribers are moving around, your cell towers are static, and then the rest of the network, once you go over the wireless links, including some backhaul, you eventually hit fiber networks, and your session, your context, as it's known, is basically pegged to a particular point of presence, which is where it exits the internet, where it exits to the internet, gets interconnected. And with Starlink, you have pretty much a similar scenario, which is you have users. Well, initially they couldn't move. The terminals had to be static. Now they support in-motion terminals. But then the cell towers, in this case the satellites, are also moving. So the topology is changing all the time. So you need a way, because of course if you have a TCP session running or a UDP packet stream, and it's going through a particular path and it's ending, let's say at the point of presence in Frankfurt or Madrid, you cannot suddenly have that traffic appearing in, say, Boston or Australia, because the connections would just break. That's just not something the internet supports as a way of operating. So the traffic always needs to be interconnected at a particular location. So how you take the traffic from a particular terminal, say in the middle of the Atlantic, you pass it through this laser mesh and eventually offload it through a gateway to the ground terrestrial network, and then from there goes through fibers all the way to, say, Frankfurt. If I am in the middle of the Atlantic and I go up to a satellite and the ISL path is broken, because one thing that we know, and I know from my simulation, is that the constellation is still not complete and there are gaps. So the mesh is not fully built, which means that at some point you're going to have a path that you're going to have to basically avoid, and you have to go sideways and then continue on a different plane and then maybe do another sideways hop. And this is shown by, for example, a test I did in Kenya. The latencies range from 40 milliseconds, which is when you had a direct path through one of the planes to a gateway in Nigeria, and then to the Lagos POP. But sometimes my latency would jump to, say, 400 milliseconds. And the only way that that's possible is that the data is taken a much longer path, either through the laser mesh, a few times around the block, so to speak, or it's being offloaded, say, in Hawaii, and then it's traveling back through submarine cables all the way to Lagos for the data streams to be maintained. So that's really the sort of things that I've been trying to check on that respect. But there's no way to actually run a trace route to anything inside the network, inside the Starlink segment. So from your terminal to the point of presence, that is basically a transparent tunnel as far as measurements can be done. So there's no real way to say, okay, let me just measure the latency to the satellite or to the gateway. The best you can do is to make measurements to the POP. That's pretty much the constraint there.
Yeah, we have been running a long-term Starlink measurements for a while now, and if you want, we can have a chat afterwards to discuss all of these internal problems. Okay.
Sure.
Any other questions? Okay, so while the audience is thinking, I can probably get my my own questions in the loop here. So, I mean, in the workshop, we had an interesting talk this morning about doing edge computing on the satellites by running things on Mars. We have had similar flavors that happened earlier in Mobicom, where people were trying to do some computations on the satellite itself rather than doing it on ground stations or on the cloud data centers. So I wanted to understand, like, what's your opinions or thoughts about in-orbit computing? And do you think it's just a thought-provoking experiment for researchers, or is it likely going to evolve into something more substantial? In that case, what can be potential good use cases for that?
Yeah, so I feel that the satellite network is about today, and the satellite edge computing is about future. So the thing is, I think we still need to explore more killer applications. So Deepak actually mentioned IoT and remote sensing. So they are existing applications, very killer applications that need in-orbit computing, because the sensing and the imaging capacity of satellite is advanced so much that the data cannot be downlinked to the ground station. So we definitely need some in-orbit computing to find more value from those data that cannot be transmitted to the ground. But I mean, those applications, they are like they are there for like decades, right? So what I'm thinking is that when we have computing in the orbital, like we are extending the computing infrastructure from 2D to 3D, right? So what kind of new applications, new killer applications we can build? So the Mars thing is wonderful, but that's like maybe 5 or 10 years later. So what I'm thinking is that maybe we need to explore more new applications. So I saw some papers, short papers, mentioning that maybe we can use this satellite as a relay for the virtual meeting or gaming across the user from all over the world. So this can reduce the network delay, but I'm not sure if it's cost effective enough. So that's, I'm not sure. So I'm still wondering if we can build such kind of applications that will become realistic in our life. Yes.
Yeah, I think I have made a very good comment about it. I would like to add several things. First of all, regarding the in-orbit computing, we have seen that recently the European Space Agency has launched several satellites with the GPU and FPGA capabilities, which basically means that it is possible for us to run some in-orbit processing tasks. I think it's primarily for the satellite image processing, for the compression, or for the object detection, and etc. So I think, especially for the low Earth orbit with advanced hardware, I think that there are some chances. I think maybe experts in this area. I just would like to add one thing about that. Another thing is that several other applications I can think of is that, for example, how about the content delivery? Because we know that we have terrestrial CDNs and we can deploy big data centers to accelerate content retrievals. But we also see that the global deployment of these data centers of CDNs are not balanced. There are some areas that we do not have immediate access to the edge servers or the data center. So that means we may have some detours. So the latency may be longer. But with these satellites, as a global infrastructure, it is possible for us to further improve our CDNs. And if you think about the resource on satellites, for example, we have computing resource, we have storage, and we also have the networking or communication resource. So I think in satellites, storage may be the cheapest one, because in the Earth observation satellite, we already have satellites with terabytes of storage. It's already there, right, to store the images. So somehow the storage resource is something that is already available in satellites, and it may be a good fit for the content delivery. I think that's something this morning we have seen several workshop papers that explore these ideas. I think there are some opportunities about that. And another possibility is that, recently we have seen several smartphones with these direct-to-cell capabilities, like iPhone, like Huawei's phones. So that basically means that we also probably want to enable some mobile communication technologies on top of the satellites, right? Some people already talk about whether we can enable the radio access network functions or core network functions in satellites. We're also exploring that. If you think about it, that basically means that in the satellites, we also need several levels of processing capabilities regarding the sessions, regarding these different contents, right? I think Google Loom also push the LTE base stations to their looms, which demonstrate the feasibility of enabling some processes inside these flight objects. I think this is also something that may be worth exploring as a case of this in optical computing.
Okay, I would like to add one thing. I think Paulo also mentioned that it's good to have some satellites open for researchers to submit their code, run in the orbital, and get results from the satellites. So actually, that's exactly what we have been doing for like 2 or 3 years. We have a small constellation called Tianshan. So we have a few satellites in orbit, and those satellites have some computing capacity. We have Raspberry Pi. We also have some ASIC-based accelerator for AI inference in orbit. And the satellite is open to the researchers all over the world. And you can submit code in a container, and you can get the results from the satellites. And yes, we have the satellite have been operating for like 1 or 2 years. We also have done some experiments about ourselves. We have obtained a lot of computing results about the energy, the CMO control in the satellites. And we actually just submitted a paper to Mobicom next year, and we are going to release that large-scale data set. We hope that can benefit the community in perspective of the in-satellite computing, edge computing.
Very cool.
Yes.
Awesome. Mike, Paulo, any opinions from your side?
Yeah, I can add some. I think that this is a giant step. Okay, we are towards a research community, so it's good to hear about this, but there are a lot of things that we need to put on the table for discussion. One of them, okay, is the resource on satellite. Yes, a satellite by default has enough space to put enough storage and nice CPUs, more than we can have in a server, in our server rack for testing. But we need to take into account that there are some space-related conditions that we don't have in our cold, nice server room, right? We need to handle the heat dissipation. We need to have very efficient energy systems. We need to to make sure that we are aware that the energy is more or less intermittent on board, right? Because if the satellite needs to power itself, it's not going to power a computing system. So these kind of things make the computing on board slightly different from what we have in the ground. The other thing, of course, is user applications. Why do we need it? Although it's really cool, why do we need it? For what kind of user applications? And this maybe can be grouped in 2 different aspects. One is space data. Data that is already in space, Earth observation, all this huge amount of small IoT CubeSats that are already launched, everything that is related with data that is generated in space, then it starts to make sense instead of downloading the huge amount of raw data to the ground that will put a lot of effort on the telecom infrastructure, being it in space on the ground. Maybe we can compute that data in space and then send the result to the ground that will occupy much less resources. This, I think, is a clear use case. But we are facing some kind of very traditional conservative business that is Earth observation. The other aspect is exactly this one, the business value. So who has more to gain with this? Okay, if you're occupying a space on a satellite that will be much more expensive to deploy and to manage, who is going to pay for it? And what kind of business is behind this? This is a new business for the satellite operators. Again, they are very conservative. Satellite operators, their business is to transport bits and bytes from one place to the other. And there are lots of different steps to be given between this current scenario and just computation on space. Okay? So the idea, the next natural step is for these networks, like I said in my first intervention, not to think about transferring bits and bytes from one place to the other, from a terminal to a ground station or between two ground stations, but actually to think about the data itself. The satellite system should be seen as a data exchange system, not just a set of pipes that can be rented. If we go in this direction, then we are going the right direction to get towards computation on space. If we are stuck in the old telecom business model of selling capacity, then we are very far away from this, independently how research evolves, in my opinion.
Interesting. Nice.
Yes, just to add to these points. I was doing some back of the envelope calculations, and assuming Starlink has, let's say, 200 gateways currently, the gateway capacity, the total gateway capacity, so for space to ground segment is around 32 terabits per second, whereas the actual capacity of the constellation is around 88 terabits per second. Whereas if you go for Gen 2, so the V2 minis that they're launching now, which technically have 4 times the capacity, that's 352 terabits per second on the constellation. And if you just add up the 100 Gbps inter-satellite links, which of course it doesn't mean that the total capacity is just that, it's just adding all of that, because once you have multiple paths, that's just the same 100 Gbps over multiple hops. But if you just add it up to, for the sake of the exercise, that's 1.32 petabits per second. Now, there's an asymmetry here between the capacity of the constellation to serve customers and the gateway capacity to actually move data to a constellation in the first place. So I do see a lot of potential research and a lot of new methods of, for example, distributed caching mechanisms, where you have a combination of very dynamic caching on board the satellites, combined with caching on the ground, but in places where CDNs are actually cheaper to operate, where you're not bound so much geographically by where you have to put the CDN, like next to the customers that you're targeting, but you can put them where, for example, power is cheap or cooling is more efficient, and then move the data through the constellation to where it needs to go. So I definitely see that once we're having these constellations up there, it enables a lot of very interesting research in some of these dynamic mechanisms for example, for content caching and delivery.
Okay. I think since we're running out of time and we need to close the session, I'll just pop one last question, which is following up on Mike's. Oh, we have a question here? Okay, Indy, please go ahead.
I want to ask a very broad question. What is one dream, this is a question for each one of you panelists. What is one dream application from an organization which you cannot run today, which requires rethinking of perhaps the infrastructure of satellite or the way in which the software stack is built? And I'm not talking about just faster processors, faster links. I'm thinking of applications that you really want to run, but you just cannot, given the way the satellite landscape will be.
Okay. So for the online audience, the question was that what's one dream application in your organizations that you want to run, but you cannot run today because of the satellite configurations, which goes beyond the faster processing and more higher capacity. Anybody wants to take this?
Yeah, maybe I can start. I think that's a fantastic question. So I can give you one example I'm currently working on. So as I mentioned that I'm currently working on the direct-to-cell satellite networks, because for the mobile operators, they still haven't entirely covered the global, right? There are still about 2 billion unconnected people in the remote underserved areas. So deploying base stations in these areas is very, very expensive. So mobile operators want to rent the satellites to offer services. But we know that, the satellites are very expensive, even for the mobile operators, right? So what they are really doing is that they want to rent satellites from satellite operators and deploy and expand their services. But the question here is that whether we can really rent these satellites and enable these 5G network services or not. I think that's a question, because in this context, we are basically having 3 players. One is the satellite network operator, the second one is the mobile network operator, and the third one is the users, right? If you look at the traditional geostationary communications, they are band pipes. So it's very easy to rent this bandwidth infrastructure, right? It's just, like the infrastructure as a service in the cloud computing. But if you look at these low Earth satellites, it moves very fast, right? And the problem here is that you have to have the access to these ground stations so that you can bridge between the satellites and the terrestrial networks. So that basically means that if you just use today's 5G protocol stacks of the infrastructure, it may not be very suitable for this direct-to-cell satellite networks, because if you are familiar with 5G, we have to build the sessions, we have to maintain a lot of states, and it's very difficult to maintain these session states if your infrastructure keeps moving around. It's very challenging. So last year we had a paper about how you can enable some stateless or connectionless cellular infrastructure so that you can simplify your satellites and so that you can easily leverage satellites to offer the direct services. I think from the networking and the cellular architecture perspective, there are definitely some cases that the current terrestrial network protocols or infrastructure may not be a good fit for this context where our infrastructure itself is moving. So that's definitely something we need to rethink about this infrastructure and see what should we do in this area.
Anyone else?
I would say I would like to see tests of optical links, so optical gateway links, so ground to space in these highly dynamic constellations, because I think if they are launching these constellations with so much capacity, at some point they're going to run out of RF spectrum to be using. Starlink is already starting to use E-band, but at some point they're going to reach the terahertz gap, and they're going to have to move to optical. So that would be mine.
Okay. Any other questions? Okay, Paulo, go ahead, please.
Yeah, I think if I understood quite right, the question is where we would like to be and compare where we are now. And one thing that I would like to see openly is what Cisco did in 2009, I think, or 8, and that was to launch an IP router in space. Without IP routers, we can stop talking, right? And the idea, that's another thing. So that will be the first step to everything that we want to develop afterwards, right? Including going towards the full-fledged or the edge computing on board. The other thing is all the discussion about 5G and non-terrestrial networks. Again, this seems simple, but it's not, right? By just what was mentioned just now about the fact that the base station is always moving. That's not what the mobile operator wants. But again, what I think I would like to see in the future is revisiting the role of satellite networks in terrestrial networks. A long time ago, satellite networks were seen as outsider, just for TV signals to be broadcasted. Currently, we are trying to integrate them on terrestrial networks. But I think we are not really being fair or truly honest with ourselves. Because if you look at the mobile operator, they don't care about the satellite network. They just want to extend the terrestrial network. So I think these problems need to be seen from the perspective of the satellite operator. What is the reason of existing of a LEO constellation like Starlink in the context of 5G? Starlink is a kind of global ISP, right? Their business is broadcast internet access, right? It's not providing mobility services, right? So where are we going to put these 5G base stations? Is on Starlink or a dedicated LEO? Or do we really need a LEO constellation for 5G? Or the mobile operators only want to relay the signal from the end user to site and then immediately back to the ground, right? Just to not to save money or extend the terrestrial network. So these are kind of the questions that can be a killer argument for the satellite business, everything that we are talking about.
All right. I think we are reaching the end of the session here, and we need to close the workshop as well. But I'm glad that we are starting these conversations here, and there were a lot more open questions that need to be discussed in this space. But for now, I would like to thank our panelists for joining us here and sharing their thoughts. And then I will hand off to Chenren to close the session.
Yeah, I think that's pretty much what I want to say. So that's the end of the workshop. I would like to thank you again for all your participation, great discussion and presentation. Let's continue the discussion over lunch, and welcome all of you to the afternoon workshop LEO-NET, right?
Yes.
On the same.
No, it's in room Colon. So it's in Colon, COLON. So we start at 2 and we continue our satellite discussions in a new workshop. So see you all there. Should be on this floor itself. Yeah, it's on the same floor. All right.
Okay.
See you guys in an hour and a half.
Thank you. Bye-bye.
Thank you so much. Bye-bye.
Thank you for having me.
Thank you so much, Mike and Paulo. Thank you.
This connection, are you thinking?